we ended talking about temperature, and that there's really three primary units within temperature. You get Fahrenheit, Celsius, and Kelvin. So one of the other big concepts that's addressed up at the top there is, what does temperature actually measure? What is it a relationship of? Okay, well, it's kind of intended to measure the average kinetic energy within an individual sample. Okay? So how fast ultimately are each of those particles moving? And we've kind of associated this weird unit of Fahrenheit or Celsius to that motion. The faster they move, the higher the temperature. Okay, so that's kind of the idea behind it. And it's the average, okay, not specific amounts of energy located within it. We could look at the common temperatures around water. So freeze for Fahrenheit, 32, and 212 for boiling. I always find this one kind of fascinating because most people know the freezing point for water being 32. But then you ask for the boiling point and most people say
212.
Really? Most people say 212?
Most people say like 300 degrees.
Oh, okay, well, I never said that. I always said it froze at 32 Fahrenheit, and then I was like, oh, it boils at 100. Not quite. It boils at 100 degrees Celsius. I don't know why I've always confused those units, but I have. Okay, so Celsius, you're freezing at 0 degrees, and you're boiling at 100 degrees. Celsius is the most commonly used, and it is most frequently used also within science. There are some times where we want to use degrees Celsius, and there's some times where we want to use Kelvin. Okay, one of the interesting features behind Kelvin. Oh, yeah, I didn't fix that. Just kind of scribble that out. One of the more interesting features of our Kelvin is that you'll notice that, actually we can't notice here. We're looking at these relatively high values, 273 and 373, some pretty big numbers in comparison to our Celsius and our Fahrenheit. Well, one of our primary driving forces behind our Kelvin is that when we get into our conversion factors, okay, what are your possible values for Kelvin? They're only positive numbers. Why might that be helpful? Because we're optimistic people and negative signs are awful. Okay? It turns out that that is actually pretty true. If you have to continue through general chemistry, the negative sign is going to be the bane of your existence. Okay? Because a simple change of your sign can take a solution from being releasing energy to absorbing energy. And that's a pretty big, significant change. Okay? So our Kelvin is kind of neat because we have no negative sign. All of our Kelvin temperatures are positive. Okay, which brings up another interesting fact. What is the lowest temperature we can get for Celsius? If Kelvin is always greater than 0, what is our lowest degree Celsius value? Negative 273 point, and you would throw in whatever decimals you want as well. We can't get any colder than that. Okay? So it's kind of a neat feature. In degrees Celsius, we've got this pretty big range. We can go negative 273 all the way up to theoretically an infinitely high temperature. Okay? Kelvin, we're only in that positive range. We don't have to worry about sign changes, which is kind of a neat thing. Fahrenheit, I did actually spend some time to read the history on it, and I've completely forgotten all the history on it, so oh well. Is just another unit form. The relationship between Fahrenheit and Celsius are given up here. You're responsible for converting between those. I personally don't have it memorized, which is why I will provide you with our degrees Celsius to Fahrenheit conversion, or that very top one. I will give that to you on the exam. I will not, however, give you the Kelvin conversion, primarily because it's relatively easy, so I kind of expect you to pick that one up. Just a sec. And then your Fahrenheit to Celsius one, that one I will expect you to derive using algebra from the original. So I'm not going to give you both. You can figure out the rest. Okay, if you need help with the algebra, I can definitely help you with that after class. It's not something I want to spend a whole lot of time on. Actually, I think the next slide has a question on it. So, yes.
Is the test open note?
The test is not open note, closed note. So what I will do is provide some information. One of those pieces of information will be a shortened, actually no, it's the full periodic table. So you don't have to keep looking up to the sides. to pick that information up. And then I will also give you little bits of stuff that I told you I'd give you. Like for this test, it's just this, I believe, just the degree Celsius conversion. Oh, and some English metric. I'll give you some of the English metric ones. I do not expect you to memorize English to metric. Metric to metric, absolutely must be memorized. You got to deal with that. And I already told you which ones are important for that. Yes, yes, yes.
So on the conversion, do we have to add the 0.15 or just?
You do not need to add the 0.15. That is not necessary. That's one of those stupid, I just happen to remember it things.
That was our questions.
Will the periodic table provided have the names and stuff, or are we gonna just?
Names? No, no names. It's pretty much a copy of what you see up on the board or on the walls. The only thing that it does not have is colors associated with it. So I'm trying to figure out the best way I can get some of that information tagged into it, because some of you in the middle might want to know what blue means. Well, for you to see what blue means in here, can you help me out? What does blue mean? Okay, read it. Can you read it off of the periodic table?
Oh, there it is.
Yeah. It takes a little bit of looking around, particularly if you're on an exam, particularly sitting in the middle, and you now turn and shift your head the other direction. What's the immediate process I'm going to say? You're cheating, okay? So I want to avoid that issue as much as possible. So I will try and come up with some starring key, perhaps. Maybe put stars or boxes or something like that around it so that you can see those extra differentiations on the periodic table that you guys have. So you don't have to sideways look to the periodic tables on the wall. That said, I can usually follow your eyesight pretty well. Yes, I've caught people cheating. Please don't make me catch you cheating. So if you need to look up the periodic tables because you're used to it, that's fine. If I suspect anything, I'll give you a warning, and then you will very quickly not be happy. Right? And neither will I, because I don't like pulling them.
Memorize the periodic table of all of it, or?
I'm giving you the periodic table, so you do not need to memorize it. What you do need to memorize are the names matched to the symbols. Okay? There's a list online that I said, these are the ones that you should memorize. And there's actually a list within the list, because there's the main list that other faculty have gone through and said are important. Then I, being an organic chemist, say most of the periodic table is useless. And I bolded a bunch of the ones that are particularly relevant for moving forward in organic chemistry. So there's still, if anybody's actually got it, you could probably count it. I think there's 10 to 16 that have been bolded, and then there's probably close to 30 to 40 on the actual list. Okay? So it's a little bit easier. It's not 118. Okay? Questions? Okay, so let's go ahead and do a conversion. I want to leave you guys to play around with it. You guys can take a swing at it and see what. I don't want to use the one on the right now, because officially, you guys don't have that. Okay, so let's look at how we would approach this problem if we only have the one on the left. So we're starting with Fahrenheit, and we need to get to degrees Celsius. Okay, so this equation doesn't quite work for us. Okay, so we would need to go through and rearrange it. There's a couple ways that you can go through and rearrange. You can plug in numbers and start your whole rearrangement process. I have found in my experiments or experience that numbers are awful. They lie to me all the time, and I don't ever want to look at them. So I will keep it as generic and symbolic as possible when I go through and solve. So before I start putting in that Fahrenheit number, I'm going to start to work with that equation, and I'm just going to use C, but for my degrees Celsius, times 9 over 5 plus 32 equals my F. Okay? I need to rearrange that somehow. I need to get C by itself so I can figure out its degrees Celsius. What do I need to do? Subtract 32 from both sides. The new equation I would get is C times 9 over 5 equals F minus 32. I still have a bunch of numbers associated with my C, so what can I do? And multiply both sides by 5. Okay, this is where we got to be careful. It's the entire thing. I would end up with C times 9, which will equal Fahrenheit minus 32 times 5. Still need to fix that. What do I do? Divide both sides by 9. And I would get as my final answer, my C equals Fahrenheit minus 32. Actually, don't let me do that quite yet. Fahrenheit minus 32 times 5 over 9. Which, conveniently enough, is the equation on the right. Okay? Good. That means I did my algebra right. That's very good. Okay? Sometimes that fails too. But usually I nail that pretty quickly. Yes? And you can use your calculators on the test as well. Remember, again, like we said, there are conversion factors hidden in calculators. I am aware of all of those conversion factors. The very easy workaround is I don't ask this as a multiple choice question. I ask this as a show your work question. You can punch it into the calculator all you want and you get the answer, but you give me no work, you get no credit. Really simple. Okay? So in this case, now that I have my equation set up where I want, I can start to plug values in. My degrees Celsius will be Fahrenheit, which was our 98.17, 98.6, minus 32 times 5 over 9. I go through and do that calculation, I'll end up with 37. Any other decimals or just 37?
37.
Oh, that's kind of nice. Degrees Celsius. Okay. So now the question becomes is why was I fishing for decimals? Officially, we have to watch out for our sig figs. This is definitely a tricky one to deal with our sig figs. How many sig figs in our starting calculation? 3 coming from that initial measurement. The next part has to do with how many sig figs in each of our stupid conversions all the way through it. Okay. If we're going to subtract 32, where do we hold our least accurate value? Okay. So we've got a subtraction here. Where do I hold the decimal? How many sig figs in the calculation after that? 2. Why 2? You get the answer correct either way, but this is why we got to be careful. Why 2? The common answer, and unfortunately that one's technically wrong. No. Addition, subtraction, what's our rule? The least accurate place, which in this case is the ones place. When I do that subtraction, I get, 70-something? Okay. There's my 2 significant digits. It's because of that least accurate location. This becomes a little bit odd, because now what happens to my sig figs in my answer? I would expect only 2 sig figs, and I've lost a significant digit. And I lost a significant digit not because of my measurement, but because of my conversion. We talked about this earlier. We want to make sure that we choose conversion factors that don't lose sig figs. Because if our conversion factor makes our answer less accurate, that's a bit of a challenge. Okay? If our calculations lose sig figs, that's one thing, okay? Or our measurements. But our conversions should be maintaining that accuracy as best as possible. So we would have to reevaluate those numbers and decide exactly what we should be subtracting in each case. I'm pretty sure that is actually supposed to be exactly 32, exactly 9, and exactly 5, which means those have infinite sig figs, and our answer should be carried to all the way out. If our 32 has infinite sig figs, there's an infinite string of zeros after it. There's an infinite string of zeros after the 5, infinite after the 9, which means my least accurate position in that first calculation is the tenths place, which means this answer would be wrong. I would need 37.0. Is this conversion absolutely 100% tricky with this whole sig figs thing? Absolutely, which is why I probably would not ask it as a sig fig question. How would I ask it?
Show your work and solve.
Could do the show your work and solve. Well, that's actually a pretty straightforward way. Actually, I would probably have to do it that way. We could say 37 degrees Celsius. I could also go through and say we did 98.6 times 9 divided by 5 plus 32, whatever that equaled. Why would I use that as an answer?
Because you hate us.
Not quite hate you, but
Because that's the,
that would be the
other conversion.
incorrect way to use the formula. You just randomly jammed numbers in and hoped it worked. And oh, look, the answer showed up, so it must be right. Okay. I would go through and do that. I would probably also give you 98.6 plus 273.1. Oh, that's a 3. 273. Why? It's yet another way to do a conversion with those numbers. Okay, so you need to make sure that you understand how to do the conversion, not just does the number show up. If you got no other choice, does the number show up is a valid way to attempt a problem. Okay? Be forewarned. Okay? I am pushing for that and will give you answers in your multiple choice that are some random amalgamation of the numbers given in the question. Okay? So you need to just not trust just that the answer shows up. You need to trust that you did the calculation right. How can you verify that? This goes to test-taking practice. Could try and work backwards, but if you made the mistake going forwards, very likely you'll make the mistake going backwards. What was that?
Plug your answer in.
Kind of plug your answer in, kind of plugging it back into the equation, but again, theoretically, you might do that again. Do the problem again. Right? Continue on the rest of the exam, come back to it, do it again. What happens if you get a different answer the second time?
Do it a third time.
You now have conflicting data. You can't actually decide on those answers. So what do? Continue on the rest of the exam. Why continue on with the rest of the exam?
Use your mind out there.
Get your brain cleared of that wrong calculation and do it a third time after you're cleared.
And so you don't waste time.
What's that?
And so you don't waste time.
And then that way you don't waste time sitting there trying to figure out what mistake you made. If you made a mistake, you will not see it. Okay? If it really comes down to it at the end of the exam, read the directions and work from there. Okay? So if you haven't looked at the practice exam, I highly recommend again that you take a look at the practice exam. Okay? Heat concept. So heat, kind of similar to temperature, except our temperature measures the average kinetic energy of our system. Our heat is more specific. Okay? It's the total energy. How much energy is in that entire thing? Not the average, but the whole system. Okay? It's often expressed with different units. So we get joules or calories. You may also see kilojoules or kilocalories. All we're doing is using a metric conversion off of those standard units. Okay? Do you need to know exactly what a joule or a calorie is?
Sure.
If you want to, go ahead. Ultimately, all I really expect you to be able to do is do any kind of conversion with it, okay, which is kind of up to you. In fact, if you push it even further, I don't really expect you to do any conversions with it either. I expect you to understand the term. Mastering will ask you to do conversions with your heat using joules and calories. Just like any other conversion. What do you want for your answer? What do you start with? Arrange any other conversion factors so that you can get your units to cancel to set you up. It tends to be a little bit more complicated because the next aspect that comes out of your heat concept is something referred to as the specific heat. When we looked at density, it was a complex unit, grams per milliliter, a relationship between mass and volume. When we move to specific heat, okay, it's an even more complex unit because now what we're looking at is an energy, joules or calories, related to grams, a mass, and a temperature change, degrees Celsius. You'll notice that the unit we use is degrees Celsius in this case. Why? Because that's when all of our theories were built. Degrees Celsius is what we were working with when we looked at specific heat. And that's why we end up using that term when we're looking at our specific heats. Okay? So we now have this big, nasty, complex unit. All we're really looking at is a way to convert between energy mass, and temperature. Right? So if I give you an energy, mass, and a temperature, can you calculate the specific heat?
Sure.
What would you do?
Use that.
Take the energy that I give you, divide it by the mass, divide it by the temperature. Ta-da! There's your answer. You've got the units to match out. What if I give you the mass and the temperature and the specific heat? What would I be asking for? So I give you the specific heat. That number there are 4.18 joules per gram degree Celsius. And then I give you 5 grams, and I say that the temperature changed by 10 degrees Celsius. What would I be expecting you to solve for? Kind of, sort of, yes, depending on what unit we were looking at. We're looking for solving for the energy, either calories or joules. How do we know which one? Question would probably say calories or joules. And then you could use either one of those conversion factors, because what's the relationship between those conversion factors? They're equal to each other. Right? So it is a much more complex unit. The mastering questions, I think, are a little bit more challenging. And I think that's mainly just because you get bogged down in all these different units. You need a lot more information to solve for this because you have more units associated with it. So it becomes a little bit more challenging. Okay? But it is the exact same format we've been doing everything else. Set up your units to cancel out. End with the units that you want. Yes?
I was going to ask, what's the difference between joules and calories?
What's the difference between degrees Celsius and Fahrenheit? It's the same thing. So they're just different energy units. Again, because when this was discovered, you were looking at people discovering these relationships independent. Because they did it independent of each other, they each came up with their own unit. Okay. Then they got together and said, I don't like you, you don't like me, I'm going to keep doing it my way, and I'm going to teach more people how to do it my way, and hopefully your way will disappear. They were both equally obnoxious about it, and neither way disappeared, and we got both.
Yay.
Yay. Way to go, science. Okay. So, what does this specific heat mean? Right? That's the more important part that we want to look at here. It is the amount of energy that we have to put in to get a given mass of sample to change temperature, to go up. Okay, so what does it mean if I have a really big specific heat? It requires more energy to do what? To raise the temperature. So is that material conduct heat or is it insulate? Okay, so we take a material, here's our little block. Here's our fire down here. That's a pretty bad fire too, if you ask me. Let's add some more color.
Fire have water in it?
No, that's the blue part of the flame, right?
Okay.
You're right, I'll erase the blue. Okay, there we go. There's our fire.
Oh, it could be a Bunsen burner.
Here's our thermometer, little bulb on top. Okay. So what we're saying, you can use your imagination. Okay. What we're saying is now we add heat to it. If I have a large specific heat, I'm saying I have to add a lot of heat to this to get the temperature to change. Was this material an insulator or a conductor? It had to insulate. It prevented the heat from passing through. That's why I had to add a ton of energy to it to actually get it to pass through. Okay. What if it was a conductor? What's going to happen to the specific heat? It should heat up very, very fast, and my specific heat should be very low. Okay. Brings up an interesting point. Remember earlier in the semester we talked about different classifications of our periodic table. What were those classifications that we've addressed?
Melting point.
Periodic table says nothing about melting point. Try again.
Well,
Metals and nonmetals, or even metalloids. Let's just keep it simple. Metals and nonmetals. Okay. What is the conductive ability for heat through a metal? Very, very good. What does that mean about its specific heat?
low.
It should be low. So how can I spin this now into a multiple choice question where we can get at the specific heat constant and not have to worry about any stupid numbers and calculations? Which of the following substances is expected to have the largest specific heat? We got a lot of different things going on in this question.
Carbon.
Right? It's actually one of my favorite questions. I like it a lot.
Oh, that's carbon.
Sure, why not? That's carbon. So we got some interesting things to process here. What we just talked about was relating it back to the periodic table and looking at metals and nonmetals and how they conduct and relate heat. Well, what's on our periodic table? What information? What do you see up there? For instance, do you see the word copper? What, please point out the word copper on the periodic table for me. Okay. The symbol is up there, not the word. So this question actually has a couple things kind of tweaked with it. Not only do you have to be able to understand something about the specific heat, you also have to be able to interpret symbols and formulas. Right? So because our periodic table, which is what we were using to look at our symbols, or look at our specific heat, has symbols, let's go ahead and switch these across to symbols. So Ca, Cr, all in symbols. What's our symbol for copper? Our symbol for, or actually we don't need lead, and symbol for carbon? C. Now that we've got them all in appropriate symbols, now we've got to try and come up with some way to understand or find some relationships between these. So there's a couple ways that we can approach this. This is kind of test-taking strategy. Right? How many of you are comfortable identifying a metal on the periodic table? Really? Oh, you're kind of hurting me. I'm kind of dying a little inside here, guys. Okay. My wings are falling off. How do we identify a metal? Left side of the periodic table, and in particular, the left side of that little staircase going down, that big bolded staircase. Anything to the left of that is metal. Everything to the right of that, non-metal. Okay, so we've got that section set up. So let's classify, we'll worry about that later. Let's classify each of these elements. Where is Ca? Left side, which makes it? What does the symbol Ca stand for? Calcium. Good answer. Cr. We got that as a metal on our left side, which is someone already jumped to as an answer. Chromium. Cu was what element? Copper. Okay, just checking, making sure. Metal, non-metal. Pb. Lead, which is a carbon, or C, which is so, with that information, which theoretically everybody should be able to do, okay, and specific heat, I'm not going to lie, I think is personally a difficult concept to grasp. Okay, but you should all be able to identify metals, and you should be able to come up with those symbols. Why is this an important thing to do? Multiple choice exam. Every time you look at your answers, you can sing yourself that little Sesame Street song. Which one of these things is not like the other? Which one of these things does not belong?
Because as large as is carbon.
So if we take a look, what's the only thing that doesn't match? Carbon. So I don't know anything about specific heat, and I know carbon's my answer. Why?
It's not a metal.
Fair enough. Let's bring it back to specific heat. It's not going to conduct heat because it's a non-metal. Our non-metals do not conduct heat. So what does that mean? The specific heat for our non-metal should be higher than all the others. There's our answer. Knowing it either through the specific heat inference or actually going through and saying which of these does not match the others. What if I'd switched it to smallest specific heat?
Nobody gets heat.
With smallest specific heat, you will notice that if I ask that question, all of your answer choices would change. Right? What would they change to? What was that?
Say it's out of letter.
I'll go ahead and leave lead up there just because you said lead.
Yeah.
What ends up being our answer choice now? Lead. Why?
Because it's not like the others.
Because it's definitely not argon.
If we're looking for the smallest specific heat now, so if that word becomes smallest, the smallest means it needs to do what with the heat? Conduct. Which material conducts heat better? Metals. Which of those is a metal? Lead. There's our answer. Okay, and you'll notice all the other answer choices are non-metals. So it's a very easy question that I can then switch and change the answers around to get at a different aspect of it, but still covering the same concept. Yes?
If all your choices were metals, is there a way to determine which one has the lowest or
All
highest specific?
of the choices were metals. Is there a way to figure it out? Yes, there is. You look it up. Yeah. Which you'll notice that they aren't perfectly trended. Not all metals have really low and all non-metals are very high. You do see some kind of fluctuations within it because they're general trends. So when it comes to an exam, somebody writing the question would say, theoretically, look up the specific heats to make sure that the answer was correct based on the actual data. And yes, somebody does that to verify that that is indeed true.
So could you like look at like the density of each one to figure out if they're all metals, which one had the highest or the lowest?
I don't know, actually. We might be able to pull that. I haven't even bothered to look at it.
I'm gonna Google that.
Yeah. Questions? Okay, what we're going to kind of drift into now is I think this is our second to last slide. Yeah. A lot of this exam is conversions. Okay? A lot of exam 3 is conversions as well. Okay? And then a large section of your final is conversions. So you got a lot of conversions running through here. And in this first exam, you get a lot of people saying, oh, I can deal with conversion, that's easy. Millis, 1,000, all that fun stuff. Okay? But we run into some issues when I switch the units to something else that you don't recognize. And that's ultimately all that happens when we move to exam 3. All the time you're doing the exact same thing, except with units that you have no clue what they mean. Right? So you can either panic and have no clue what they mean, or you follow the same dimensional analysis system that we've been working on to allow you to solve that. Which is why every time that we've gone through and worked a problem, I've been asking you to set up that format. What do you want as an answer? What are you given? We now need to do a conversion factor. That conversion in between has to get rid of those units. If we're lucky, it does it in one step. If we're not lucky, we have to do it in multiple steps. Okay? So when it comes to this exam, yeah, I potentially can't use those crazy units that we talk about in chemistry. But I can make up all sorts of units I want. How many meeks are in 3.4 stops? This stops. Anybody?
12.
I don't know actually, what is it? We'd need a conversion factor. We need the conversion factor between meeks and stops. So what we could do is set up again our question, how many meeks, so we're trying to get to MKS.
These real measurements?
I don't think so. I mean, it's possible. I did just make them up, you
Abbreviations
know.
of these ones, I was like,
Monkey at a typewriter making Shakespeare eventually. 3.4 stops. All I'm trying to do is get those units to equal each other. STP needs to cancel. I need meeks on top. Do I have a conversion factor between stops and meeks? Yeah, that information is given to me either in the question or where else could it be found on your exam? The front of the exam, the very first page of your exam will have that periodic table, place to write your name, and some conversion factors for English to metric. Okay? I will try, actually I don't even have to try, it's already posted. The practice exam that you've got has those units on it. Okay? That is information you do not need to memorize. I will give that to you. Anything that's not on that, you should either ask me about before the exam starts, so it makes it onto the exam, or you accept memorizing it. Those are your two choices. So, how do we solve this?
Put 4.5 times 10 to the third on the bottom.
Try again.
My bad.
4.5 times 10 to the third in front of stops, not on the bottom.
In the denominator, I'm sorry.
In front of STUPS. It has nothing to do with the denominator either. It's in front of the unit.
Okay.
1 in front of our meeks. Our STUPS cancel, we'd have our meeks. Do we need to know anything about what a meek or a STUP is? No clue. Okay? Completely irrelevant. That's the power of dimensional analysis. You can do a calculation and have no idea what it means. Okay? That's a good thing. Ish. Okay? Questions? Okay, breakdown on the exam. I am panicked about trying to get the exam done on time. This means I am using the old exam as a template to build the new exam. Okay? A lot of people seem to get excited about that. Be careful. Just because it looks like the same question does not mean I'm asking the same question. I can change one word and it goes from trying to look at, say, perhaps wherever it went, carbon to something else. So a very simple change in the question can change your answer. Because I am obnoxious like that, I will probably put the old answer on there. Okay? So make sure you answer the question that's asked, not the question that you hope I asked from the old exam. Right? I am going to try and shuffle the answers around and shuffle the questions within a little bit so that you don't kind of fall into that pattern, because I don't want you doing that. The other reason why is I'm trying to tell you now, don't just say, oh, I answered this question already. Okay? Check the numbers, check your work, go through and answer the question that's asked. So read the exam carefully. I do kind of apologize for that, but that's the best that I can kind of go through and do.
Should specific heat be on there?
Specific heat will be on there. Hence the whole statement of this is a pretty good exam question. Okay. I don't think this exact one is on there.
I mean,
But
like the calculation.
the calculation for specific heat, no. No, I think that's kind of a meaningless calculation. That exact question's on the practice exam? Okay, well. Doesn't mean it's on the final, or this exam. Okay, so I am going to go ahead and stop the recording.